There is exactly one company on Earth that can build the machines that print the world's most advanced computer chips. It's called ASML. It sits in a small town in the Netherlands, and the entire reason it holds that kind of power comes down to a single part almost nobody outside the industry can name: the light source. Not the machine, the light. Then, in February of 2021, a team of physicists working across 3 countries, China, Germany, and the United States, published a result in the journal Nature that pointed toward a completely different way to make that exact same light, a way that, at least in theory, doesn't need ASML at all. It is the one thing this 60-year monopoly in miniature was never built to survive. Around the same time, a separate and far more visible Chinese effort was taking shape a few thousand kilometers away. A domestic prototype EUV machine, built the hard way, brute force style, reportedly sprawling across an entire factory floor several times the physical footprint of an ASML scanner, which is roughly the size of a school bus. Some engineers, half joking, started comparing the national effort behind it to China's own Manhattan Project. 2 very different Chinese bets. One quiet and theoretical, running through a particle accelerator in a Berlin physics lab. One loud and industrial, running through a factory floor somewhere in China. Both aimed at the exact same target: 13.5 nanometers of light, the single hardest kind of light humanity has ever learned to manufacture on purpose. I'm a semiconductor engineer, and when I started digging into both of these stories, I expected a fairly familiar plot: reverse engineering, stolen blueprints, sanctions being quietly routed around. What I found was stranger and more interesting than that. What surprised me most wasn't what China copied. It was what it chose to do differently twice, in 2 completely unrelated ways, at almost the same time. So in this video, we're going to take ASML's actual monopoly apart piece by piece: the machine, the light, the mirrors, the money, and then look at both of China's answers to it side by side. The brute force prototype trying to outmuscle physics with scale, and the strange particle accelerator alternative trying to sidestep physics entirely. By the end, you'll understand exactly why one analyst put it as bluntly as this: this company has the market completely cornered, and you'll understand exactly what it would take to uncorner it. Every advanced computer chip on Earth is made the same basic way. Light gets shown through a stencil, called a mask, and the pattern gets projected down onto a silicon wafer coated in a light-sensitive chemical. It's photography, essentially, except the photograph is a microscopic circuit, and the smaller you want that circuit to be, the shorter the wavelength of light you need to draw it with. Ordinary visible light isn't remotely sharp enough. The most advanced chips being manufactured today are printed using light with a wavelength of just 13.5 nanometers, extreme ultraviolet light, or EUV for short. For comparison, that's roughly 40 times shorter than the light your eyes can actually see. And here is the entire problem in one sentence: light that's short does not meaningfully exist anywhere in nature, in any usable, controllable form. You cannot buy an EUV light bulb. There is no mineral you can mine for it, no gas you can burn for it. You have to manufacture the light itself, from scratch, on demand, thousands of times a second, for years without stopping. That turns out to be one of the single hardest engineering problems the semiconductor industry has ever had to solve, harder in a lot of ways than the chips themselves. Here's how ASML actually does it, and I want you to genuinely sit with how insane this is, because it explains almost everything that follows. Inside the light source, a generator fires a continuous stream of molten tin droplets, each one about 25 microns, across roughly a quarter the width of a single human hair. Those droplets fall through a vacuum chamber at around 70 meters per second. As each droplet falls, a laser hits it, not once, but twice. The first pulse, a smaller and weaker one, flattens the droplet into a thin, wide pancake shape, because a flattened target is easier to vaporize evenly than a sphere. A split second later, a second, far more powerful pulse slams into that exact same flattened droplet and instantly turns it into plasma at somewhere around 200,000 degrees Celsius hotter than the surface of the sun by a wide margin. In that fraction of a second, as the dying tin plasma cools, it emits a flash of 13.5 nanometer EUV light. Then the entire sequence repeats 50,000 times, every single second, for months on end, without missing. Read that back slowly, because that number is the whole story. 50,000 microscopic falling targets a second, each one hit twice, with total precision, continuously, inside a machine that has to keep doing this reliably for years. Miss even a small fraction of those shots, and you don't get a slightly dimmer picture, you get a defective chip or no chip at all. The laser responsible for that second plasma-triggering pulse is its own small miracle. It's a carbon dioxide laser built by the German firm Trumpf, and it starts out as an unremarkable beam carrying just a few watts of power. That beam then gets amplified more than 10,000 times across 5 separate amplification stages, until it's carrying tens of kilowatts of average power, with peaks reaching into the megawatt range. Also, it can strike a falling speck of tin at exactly the right microsecond, tens of thousands of times a second, month after month, without ever drifting out of alignment. When national labs like Lawrence Livermore first started seriously researching EUV back in the 1980s, plenty of respected physicists thought the whole idea was simply impossible, not just impractical. It took the wider industry roughly 30 years and tens of billions of dollars to prove them wrong. ASML didn't invent every piece of this alone, either. The lasers come from Trumpf. The mirror is some of the flattest, most precisely engineered surfaces ever manufactured by human beings come from another German company, Zeiss. The plasma source technology itself traces back to a California company called Cymer, which ASML eventually bought outright. What ASML actually owns, in the end, isn't any single invention. It's the accumulated, patented, export-controlled knowledge of how to make all of these separate, impossible pieces work together, in sync, 50,000 times a second, for thousands of hours, without failing. That 30-year head start is the actual thing every competitor on Earth is now racing to catch up to. There's also a filthy, expensive cost hiding underneath all of this elegance. Firing 50,000 tiny tin explosions a second inside a sealed chamber is a genuinely dirty process. Tin vapor and debris coat every surface inside it. To keep that manageable, the chamber has to be constantly flooded with hydrogen gas just to sweep the mess away, and even then the collector mirror slowly degrades over time regardless. The whole machine needs constant, expensive servicing simply to keep the light clean enough to use. And every hour a light source spends being serviced is an hour, a tool worth hundreds of millions of dollars, sits there printing nothing at all. Hold on to that detail. It matters again later, on both sides of this story. Generating the light, somehow, still isn't the hard part. Because now you have to actually focus that flash of impossibly short wavelength light onto a silicon wafer with atomic precision. And here's the second problem hiding underneath the first one. Glasses, cameras, microscopes, telescopes, virtually every optical instrument humans have ever built relies on lenses, bending light through curved glass. An EUV machine cannot use a single one. At 13.5 nanometers, almost every material simply absorbs the light instead of bending it. Glass doesn't refract it, glass swallows it whole. So the entire optical path inside an EUV scanner is built out of mirrors, instead a relay chain that bounces the light stage by stage until it finally lands on the wafer. But these aren't ordinary mirrors. Each one is built from dozens of atomically thin, alternating layers of molybdenum and silicon, engineered to reflect a wavelength that almost nothing else on Earth will reflect at all. And even these specialized mirrors are lossy. Every single bounce off one of them throws away roughly 30% of the light that hits it. By the time a beam has bounced its way through the whole optical chain to the wafer, only a small fraction of the original flash survives, which means the light source upstream has to be wildly overpowered just so a usable amount makes it to the finish line. There is almost no room for error anywhere in that chain, and every mirror in it has to be polished and aligned to a smoothness measured in fractions of an atom's width. Building mirrors like that is extraordinarily hard. Measuring and aligning them turns out to be even harder. For decades, there was exactly one place on the planet that fully knew how to do it: Zeiss. Not because of one clever patent, but because the company spent more than 30 straight years perfecting every individual step, polishing, coating, measuring, aligning to a level of precision that essentially nobody else in the world has ever matched. That is the actual difference between building a mirror and building an EUV mirror. Put all of that together, and you get a machine unlike almost anything else humans manufacture. ASML is the sole producer of EUV lithography machines on the entire planet. Not the leading producer, the only one. There is no second supplier anywhere in the world to shop around with. A standard EUV scanner already costs upward of $200 million. The newest generation, the high numerical aperture machines with even bigger optics, run around $380 million each, roughly double. That's the price of one tool. And to manufacture a single leading-edge chip, whether it's the processor inside the phone in your pocket or the accelerators training the AI models everyone's talking about right now, that pattern has to pass through an ASML machine at some point in the process. There is no other door into that room. That position has pushed ASML's market value past $670 billion, a European record. When CNBC once asked Chief Executive Christophe Fouquet what, realistically, was stopping the company from charging even more for its machines, he essentially conceded that they hold every card at the table. Daniel Newman, an analyst at the Futurum Group, put it more bluntly than that. This company, he said, has the market completely cornered. So that's the board, laid out in full. One company, one almost impossibly hard light source to manufacture. An entire generation of global technology, phones, cars, data centers, artificial intelligence bottlenecked through a handful of factories in one small country. And that is exactly why the two Chinese efforts we're about to walk through matter as much as they do, because the entire American and Dutch strategy for slowing China's chip industry down rests on a single, specific assumption: that this light source is so hard to build that nobody can recreate it in secret, and nobody can quietly go around it. Block the machine, the thinking goes, and you block the chips. That was the whole theory of the case. Both of China's answers, in completely different ways, are direct tests of whether that theory still holds. Let's start with the loud, visible one: China's own domestic prototype EUV scanner, the machine reportedly sprawling across an entire factory floor, the one people started jokingly comparing to a national Manhattan project. China's first challenge, unsurprisingly, was the same one ASML solved first: build the light source. Publicly available reporting suggests China is actually attacking this from two directions at once. The first is a straightforward attempt to replicate ASML's own approach, laser-produced plasma, or LPP, the exact tin droplet, double laser pulse method we just walked through. That, on its own, is a monumental undertaking. Hitting 50,000 microscopic moving targets a second without missing, using a laser architecture, nobody outside, a small circle of Dutch, German, and American engineers has ever fully industrialized. The second direction is stranger and more interesting, because it isn't really new. It's an old idea China is betting has finally come of age. It's called laser-induced discharge plasma, or LDP, and instead of chasing 50,000 flying tin droplets a second, it starts from a completely different piece of hardware. Picture two metal discs, rotating slowly, each one sitting partly submerged in a bath of heated liquid tin. As the discs spin, a thin coating of tin builds up on their surface. Those discs double as electrodes, wired into massive banks of capacitors sitting there fully charged, waiting. A small laser fires at one of the discs. That's the trigger, not the main event. It vaporizes a tiny amount of tin off the surface, creating a small cloud of tin vapor hanging in the gap between the two disks. At that exact moment, the capacitors dump their entire stored charge, and a huge electrical current jumps straight through that cloud of vapor. The current generates its own magnetic field, and that field crushes the vapor inward into a plasma that's incredibly hot and incredibly dense, hundreds of thousands of degrees. And that plasma, just like ASML's tin droplets, emits 13.5 nanometer EUV light. Same light, radically different machine. And on paper, LDP has some genuinely compelling advantages. No giant carbon dioxide laser cascade to build and maintain. No need to hit 50,000 flying droplets a second with zero margin for error, which means a much higher hit rate and, potentially, a simpler and cheaper machine overall. So why didn't ASML just build it this way in the first place? Because 20 years ago, they actually tried and hit a wall that had nothing to do with cleverness and everything to do with physics. The challenge was never creating EUV light through this method. It was creating enough of it, fast enough, to matter. A working fab needs hundreds of watts of stable EUV output, because without that kind of power, every single wafer takes too long to expose to be commercially viable. It's a bit like trying to cook dinner using only the heat coming off a light bulb. You might technically get there eventually, but no factory on Earth can afford to wait that long. The LDP approach, historically, hit a specific physics wall. As engineers pumped more energy into the plasma to boost output, the plasma simply grew larger, not brighter, and the collecting mirror behind it couldn't gather up most of that extra light anyway. You could keep adding power indefinitely without meaningfully increasing the amount of usable EUV light coming out the other end. Eventually, ASML just moved on. Not because the LDP approach was fundamentally impossible, but because 20 years ago, it couldn't be scaled to real manufacturing. As a result, that older approach topped out at around 30 watts of output power, while ASML's latest LPP-based prototypes are now reaching past 700 watts. So ASML switched and never looked back, because at the time, this second path was simply impractical. And here is the very important distinction hiding underneath China's decision to revisit it anyway. China isn't betting that LDP was secretly the smarter approach all along. It's betting that 2026 isn't 2006, that better capacitors, better magnetics, and better materials, science might finally push a 20-year-old dead end back open. Public reporting suggests China has now demonstrated working prototypes of both approaches, conventional LPP and the older LDP method, and continues actively developing both in parallel. The output power and yields on either path are still reportedly well below what high-volume manufacturing actually requires. But for the first time, China has built its own functioning EUV light source, using two different bets on how to get there instead of one. At this point, it would almost feel like the hardest part was already solved. It wasn't. Because now, just like ASML 60 years into its own journey, China had to focus that light. And the mirror problem turns out to be every bit as brutal the second time around. Here, the effort centers on an institution called the Changchun Institute of Optics, Fine Mechanics and Physics, part of the Chinese Academy of Sciences, which has spent decades building genuinely world-class optics, including instruments for space telescopes. But an EUV mirror is a different animal entirely from anything else in that portfolio. The surface has to be smoothed to somewhere around 50 picometers, smaller than the width of a single atom. That level of polish, on a curved, multi-layer coated surface, is essentially Zeiss's core secret, refined over more than 30 years, and even verifying that a mirror meets the standard requires measurement tools that barely exist anywhere outside Zeiss's own labs. And the challenge doesn't end once a mirror is built and installed. Inside a running EUV scanner, mirrors sit directly in the line of fire of hot tin plasma debris and intense EUV radiation, hour after hour, year after year. Keeping their reflective coating stable under that kind of bombardment, for years inside a productive machine, is its own separate engineering discipline. Public reporting suggests Chinese institutes have already demonstrated domestic EUV mirrors and integrated them into working prototype optical systems. Matching Zeiss, however, is a completely different challenge, not just in raw optical quality, but in reflectivity and long-term durability after decades of accumulated production experience that China simply doesn't have yet. So China appears to be making a very specific, very deliberate engineering trade-off. If your mirrors are less efficient than the world's best, and your light source is dimmer than the world's best, one of the only ways to compensate is with sheer scale. Bigger collectors, bigger lasers, a longer optical path, larger mirrors throughout. It's the engineering equivalent of saying, if you can't make it more precise, make it bigger instead. That trade-off may explain, better than any single technical detail, why China's prototype reportedly occupies an entire factory floor, while an equivalent ASML scanner is roughly the size of a school bus. Reports suggest the Changchun Institute has now integrated a fully domestic optical system into China's prototype scanner. That does not mean China has matched Zeiss's quality, far from it. Overall, optical performance reportedly still sits well below commercial EUV scanners. But it's still a genuine milestone, because for the first time, China appears to have assembled an entirely domestically developed optical system capable of actually operating inside a working EUV scanner. And that brings us to a bottleneck almost nobody expects, because it isn't something you can polish, align, or out-engineer at all. It's helium, the same gas that fills party balloons, and, somehow, one of the most sophisticated machines humanity has ever built cannot run without a steady supply of it. Helium is essential both inside EUV tools and across chip manufacturing more broadly, because nothing else can do all of its jobs at once. It carries heat away from some of the hottest, most delicate parts of the process. It doesn't chemically react with sensitive optics or with the silicon wafers themselves. And its atoms are so small that it's used to detect leaks too tiny for any other gas to reveal. Take helium away, and chip production simply stops with it. There's no practical substitute waiting in the wings. EUV machines don't sip helium either. They drink enormous amounts of it. A single advanced fab can require somewhere between 5,000 and 20,000 cubic meters of it every single month, which creates a real problem for China specifically. It reportedly imports roughly 85% of the helium it uses. Domestic production sits under 900 tons a year, while imports reportedly exceed 4,900 tons, and historically, most of that supply has come from just two countries, Qatar and Russia. Both of those supply relationships have come under real pressure in recent years. And unlike oil, helium can't simply be stockpiled indefinitely. It's transported as a cryogenic liquid, and it's extremely time-sensitive. Delay a shipment long enough and it slowly boils away on its own. Once it escapes into the atmosphere, it's gone for good, with no getting it back. Meanwhile, the world's largest known helium reserves happen to sit somewhere else entirely, in the United States and in Qatar. And to be clear, this isn't only China's problem. It's everyone's problem: TSMC's, Samsung's, Intel's, SK Hynix's. Essentially, every advanced semiconductor manufacturer on Earth draws from the exact same fragile global supply chain. China, specifically, is now trying to build an entirely domestic EUV ecosystem while still depending heavily on a material it doesn't fully control, which reportedly led Beijing to impose an emergency restriction on helium exports in order to hoard what supply it does have for its own chip factories. The deeper you get into this story, the clearer it becomes that an EUV scanner isn't limited by any single invention. It's limited by thousands of interlocking, mostly invisible dependencies. Some of them are billion-dollar mirrors. Some are 30 years of accumulated optical know-how, and some, apparently, are just a colorless gas that almost nobody thinks about twice. But even if you solve the light, build the mirrors, and secure the helium supply, one challenge still remains, and it might be the hardest one of all: the people who actually know how to make every piece of it work together as a single reliable system. because there is exactly one thing sanctions and export controls could never fully stop, and that's knowledge. You can block a machine at a border, you can block a component on a shipping manifest. You cannot block what's already living inside someone's head, and that may have been ASML's quietest, deepest advantage all along. So China hasn't only invested in labs and research institutes. It has actively invested in experience, recruiting some of its best engineers working overseas back home into some of the country's highest priority technology programs. One frequently cited example is a physicist named Lin Nan, who reportedly spent years at ASML directly working on the EUV light source, arguably the single most demanding subsystem in the entire machine. After returning to China, he joined the Shanghai Institute of Optics and Fine Mechanics, where his team reportedly began rapidly publishing research and filing patents related to EUV light generation. And the sheer scale of money and talent China is throwing at this problem is starting to show up in the data. Look at research publication counts on EUV lithography over time, and a clear pattern emerges. For years, Chinese output in the field was relatively thin. Then, around 2020, it suddenly takes off, as dozens of separate teams start attacking different pieces of the same problem in parallel. So where does all of that leave the loud, visible prototype? Reports suggest China now has a working EUV prototype currently delivering somewhere around 100 watts of output, while ASML's production systems deliver roughly 300 watts today, with the newest prototypes reaching as high as 700. That's still a substantial gap, 3 to 7 times, depending on which ASML machine you compare it to. But does China actually need to match ASML watt for watt? I don't think it does. Right now, SMIC manufactures its most advanced chips using something called quadruple pattern deep ultraviolet lithography, an older generation of technology that compensates for the lack of EUV by running the same wafer through the lithography machine 4 separate times to build up a fine enough pattern. It works, technically, but the yields fall below 50%, time and cost rise dramatically with every extra pass, and eventually physics simply refuses to cooperate any further. You cannot keep shrinking transistors indefinitely using that trick. It will not get you to a 5 nanometer class equivalent process node, which means a domestic EUV machine doesn't have to become the best EUV machine in the world. It only has to become better than the alternative currently sitting on the factory floor. Even if it prints fewer wafers per hour, even if it's nowhere close to commercially competitive on cost, even if its yields sit far below ASML's, if it can simply replace quadruple pattern DUV, that alone would already be a massive win for China's entire semiconductor industry. And remember, ASML itself needed roughly 12 years to go from its very first EUV prototype to an actual shippable commercial product. China will almost certainly need real-time too, but unlike ASML's journey, this was never purely a commercial project to begin with. It's a strategic one. The goal was never necessarily to build the best EUV machine on Earth. The goal is to build one China fully controls, on its own soil, answerable to no export license. And after that comes the part nobody can shortcut with money or ambition alone. Turning a machine that works once in a lab into a factory tool that runs 24 hours a day, printing hundreds of wafers an hour for years without falling over. The distance between those two things is enormous, and it's the same distance ASML itself spent 3 decades closing. That's the loud bet, heavy, industrial, visible from space, essentially trying to outmuscle ASML's own approach through scale and sheer persistence. But at almost the exact same time, a much quieter Chinese effort was taking a completely different route to the same destination, and it's the one that should actually worry ASML the most. To understand it, forget tin droplets entirely. Picture instead a ring, a racetrack for electrons, called a storage ring, the same basic kind of particle accelerator you'd normally only find inside a national physics laboratory. You take a beam of electrons, accelerate them to nearly the speed of light, and send them looping around that ring, over and over, indefinitely. Normally, The electrons inside a beam like that are spread out into long, loose clumps, roughly a centimeter long, spaced something like 60 centimeters apart. Loose clumps like that produce ordinary synchrotron light, genuinely useful for scientific research, but nowhere near powerful or tightly focused enough to print chips at any kind of volume. The idea a Tsinghua University team has been chasing is a way to squeeze those loose clumps into something far more extraordinary. Using a carefully tuned laser inside a device called an undulator, they nudge the circulating electrons so that after one full trip around the ring, they snap into incredibly tight, evenly spaced microbunches, each one only about a single micrometer long. When electrons are packed that tightly and that regularly, something remarkable happens to the light they give off. Instead of radiating messily, like an ordinary light bulb, they start radiating coherently, like a laser. All their individual light waves line up with each other. And because the electrons keep circling the ring continuously, they keep doing this in a steady, unbroken state, rather than in violent little bursts. That steady, continuous quality is where the whole concept gets its name, steady-state microbunching, or SSMB. Now, put that next to ASML's approach for a second, because the contrast is really the entire point of this story. ASML's light source is, in effect, a strobe light. 50,000 separate, violent little explosions of light every second, along with all the tin debris and expensive downtime that come bundled with them. The SSMB approach doesn't explode anything at all. No molten tin, no falling droplets, no debris to constantly sweep out of a sealed chamber, just a beam of electrons, circling a ring, gently coaxed into producing a smooth, continuous, laser-like river of extreme ultraviolet light. And on paper, the numbers this approach promises are genuinely staggering. The peer-reviewed research describes SSMB as a credible path toward kilowatt-level average power in the EUV range. For comparison, ASML's current production light sources put out a few hundred watts of usable power, and the company is spending the rest of this decade fighting hard just to reach 1,000 watts by around 2030. SSMB is aiming at that same ballpark from a completely different starting line, using completely different physics. And there's a reason raw power matters this much here, a detail that rarely gets properly explained. Remember that 30% loss on every single mirror bounce we walked through earlier? Professor Chuanxiang Tang, who leads the Tsinghua effort, has pointed out that light inside one of these machines can bounce roughly 11 separate times on its way from the source to the wafer. Do that math yourself. After 11 bounces at 30% loss apiece, only a small sliver of your original light survives all the way to the silicon, which means you have to start with an almost absurd amount of power just to end up with barely enough at the finish line. That compounding loss is the exact wall ASML's tin droplet strobe keeps slamming into as it tries to push past current power levels. A continuous, laser-like source is one very direct way to blow straight through that wall instead of fighting it head-on. Here's the part that should genuinely make you sit up. A single one of these accelerator rings wouldn't have to feed just one lithography machine. Because the electrons are circling a large physical loop, you could, in principle, place multiple lithography exposure stations all the way around the outside of that ring, like workbenches arranged around a central sun, and feed every single one of them from the exact same shared source of light. One national-scale light source, powering an entire fabrication complex at once, instead of one dedicated light source bolted onto every individual machine. In the Chinese press, this vision has already picked up a nickname that tells you almost everything about how it's being received. People are calling it the lithographic cannon, and that nickname points at something that flips ASML's entire economic model in a way that's easy to miss at first. ASML's business is built around one giant, delicate, extraordinarily expensive light source, permanently bolted to one single scanner, sold as a complete package for hundreds of millions of dollars, one machine at a time. A shared storage ring rearranges that completely. You build the single hardest, most expensive component, the accelerator itself, exactly once, and then you hang comparatively simpler exposure stations off it, as many as the ring is physically capable of feeding. If that model ever works at real production scale, the single most expensive piece of the entire system gets spread across an entire floor of machines instead of loaded separately onto every one of them. And ASML's pricing power, the thing propping up that $670 billion valuation, suddenly starts to look a lot more fragile than anyone assumed. Now, I want to be genuinely honest about where the credit for this actually belongs, because a lot of the coverage around this story gets tribal and dumb very quickly, and that does a disservice to what's actually a much more interesting, much more international story. This is not some secret Chinese invention that appeared out of nowhere. The core idea behind steady-state microbunching was first proposed around 2010 by an American physicist, Alexander Chow, one of the most respected accelerator physicists alive, based at SLAC, together with his graduate student, Daniel Ratner, at Stanford. They published the concept, and then, for years, the theory largely just sat on paper because nobody had access to a machine specialized enough to actually go test it on. What changed the trajectory was a young Tsinghua University physicist, Xu Jiedeng, working on his doctorate under Professor Tang, who took Chow's original idea and pushed the underlying mathematics much further than anyone had before. Chow himself personally helped connect the Tsinghua group with accelerator physicists in Germany, and together with Germany's National Metrology Institute, the PTB, and the Helmholtz Zentrum Berlin, the collaboration finally gained access to a machine special enough to actually attempt the experiment. And this is the twist. Most of the surface-level coverage of this story skips entirely. The experiment that proved this idea could actually work did not happen inside China at all. It happened in Berlin, on a German storage ring called the Metrology Light Source, the first ring anywhere in the world specifically designed to run in the unusual operating mode that SSMB requires. In February of 2021, that genuinely international team, Chinese, German, and American physicists working together, published their result in Nature, one of the most rigorous, most selective journals in all of science. They had actually done it, taken a real, physical electron beam, forced it into those tight micro bunches, and made it radiate exactly the way the underlying theory predicted it should. It was what physicists call a proof of principle, the crucial, difficult step that takes an idea from 0 to 1. And that single result is what turned SSMB from an elegant equation sitting in a physics journal into something the entire global semiconductor world suddenly had to start taking seriously. So why does one experiment on a research accelerator in Berlin keep semiconductor strategists in Washington and The Hague awake at night? It comes down to understanding what a monopoly like this actually is, underneath all the machinery. ASML's power was never really about being better at manufacturing chips than everyone else on Earth. It was about owning the one single road every chip maker on the planet had to travel to get there. Every sanction, every export control, every choke point that the United States and the Netherlands built over the last several years assumed that road was the only road that existed. Full stop. Those controls were engineered carefully to guard one specific road, ASML's machine. They were never designed to handle the possibility that physics might quietly offer a second road to the exact same destination. If China, or frankly anyone else, can eventually generate usable 13.5 nanometer light from a ring of circulating electrons instead of a cloud of exploding tin, then an enormous share of those export controls are suddenly aimed at the wrong target entirely. They're carefully guarding one locked door while somebody 100 meters down the wall quietly cuts an entirely new one through the brick. That is what ASML should fear most, not a rival that plays the exact same game slightly worse, but one that simply refuses to play the game at all. Now, before this runs away with itself, I promised you honesty earlier, and here's the cold water, because it genuinely matters. That 2021 experiment demonstrated a physical mechanism. It did not build a working chip factory, and the distance between those two things is enormous. Anyone telling you the monopoly is already finished is, frankly, selling you something. In that original proof of principle setup, the electron bunches carried only a tiny fraction of the total charge a real, high-power industrial source would eventually need. Turning a delicate laboratory demonstration into a machine that reliably prints millions of chips a year with almost zero defects is a completely different mountain to climb, arguably a taller one than the demonstration itself. And here's the genuinely sobering part for anyone rooting hard for a fast upset. Remember that ASML's own journey, from EUV being dismissed as flatly impossible to an actual working production machine, took roughly 30 years. China, effectively, is starting that same clock now on the light source alone. And the light source, as we've already seen twice over in this video, is just one component out of hundreds of thousands inside a working machine. Researchers at Europe's Inter-University Microelectronics Center, IMEC, point to what they call the yield gap as the single hardest part of all. The brutal distance between making beautiful, powerful light inside a research lab and actually printing millions of commercial chips where almost none of them come out defective. You can build the most powerful, cleanest EUV beam ever produced and still fail completely if your mirrors are misaligned by a single nanometer or if your photoresist chemistry isn't tuned exactly right. That specific part is the part that money genuinely cannot shortcut. It takes years, repeated failure, and roughly a decade of hard-won institutional learning that can't be downloaded, stolen, or bought outright. There's also a very simple reason none of this has already happened somewhere else first, and it isn't that Western engineers were asleep at the wheel. Building a storage ring is a massive undertaking in its own right. According to plans reported by the South China Morning Post, the proposed facility for a production-scale version of this ring, planned for China's Jiang'an New Area, would measure somewhere between 100 and 150 meters around. That is a piece of national infrastructure, closer in scale to a small particle physics laboratory than to a product you roll off a factory assembly line. And even the underlying physics still has genuinely open questions sitting unanswered. Getting from a single successful demonstration in Berlin to a stable kilowatt-class EUV source that runs reliably 24 hours a day inside a working factory is at an absolute minimum years of extremely hard engineering work, and it could still hit some entirely new wall nobody has even discovered yet. But none of that lets ASML fully relax either, and the reason is simple. China is not the only one who noticed this result. In the United States, a startup called X-Light is chasing a closely related idea of its own, using a large particle accelerator and a free electron laser to generate EUV light and pipe it into existing lithography scanners. Serious money and serious physicists on both sides of the Pacific have quietly arrived at roughly the same conclusion at almost the same time. The tin droplet strobe light, miraculous as it genuinely is, might not turn out to be the final answer after all. The future of the single most important light in the modern world might, eventually, belong to particle accelerators instead of exploding metal droplets. And the moment that stops being a maybe and starts being a when, ASML's decades of hard-won, deeply specialized advantage in tin plasma engineering stops functioning as an unbreakable moat and starts looking more like a very sophisticated, very expensive head start. Think about what a cheaper, higher power, structurally cleaner light source would actually do to the underlying economics of the entire industry. Right now, every single wafer that comes out of a leading-edge fab carries a slice of that $380 million machine cost baked directly into its price. On top of all the expensive maintenance downtime that comes from constantly sweeping tin debris out of a sealed chamber, the entire industry, as it exists today, is organized around engineered scarcity. A small number of these tools, all sourced from exactly one supplier, rationed out to the handful of companies on Earth that can actually afford them. crack that light source open using a genuinely different physical process. And the effect goes far beyond simply helping one country catch up. You threaten the scarcity itself, which is the exact thing that makes ASML worth $670 billion in the first place. Some analysts have already started sketching out a future in which advanced chip making effectively splits into two separate technological tracks. A Western one, built entirely around ASML's tin droplet EUV, and a Chinese one, built around particle accelerators and brute force domestic workarounds. Whether or not that full split ever actually happens, the fact that it's even a plausible conversation to have out loud is itself the real shift. For 20 straight years, there was, for all practical purposes, exactly one path to a cutting-edge chip on Earth. That is only just starting to change. If you're getting genuine value out of this breakdown, do me one favor and subscribe, because this channel goes deep on exactly these kinds of stories. The technologies quietly deciding who wins the next decade, long before they ever make it into the mainstream news. Leverage, in the end, is really the word that matters most in this entire story. For years, export controls worked, in large part, because everyone involved genuinely believed they were airtight, that there was simply no way around ASML, full stop, end of discussion. The moment a credible alternative exists anywhere in the world, even one that remains a full decade away from a working factory, that underlying belief starts to crack, quietly, at the edges. It changes how China negotiates. It changes exactly how hard the West can afford to squeeze before pushing its rivals to finish building their own parallel technology stack out of sheer necessity. And it changes how comfortable the world's chip makers genuinely feel betting their entire future roadmap on a single supplier, sitting inside a single small country forever. Those controls always leaned heavily on everyone's shared confidence that there was simply no way around ASML, and steady-state microbunching doesn't have to print a single commercial chip to start quietly eating away at that confidence anyway. That is also, not coincidentally, why the money is moving the way it currently is. China has reportedly poured the equivalent of tens of billions of euros into building an entire domestic lithography ecosystem from the light source upward, and the SSMB effort is widely considered one of the genuine crown jewels of that broader push, sitting right alongside the louder, more industrial LPP and LDP prototype effort we walked through earlier. The point, underneath all the individual numbers, is really the sheer scale of the ambition on display. That kind of sustained, multi-track spending is a bet on the entire next generation of lithography technology, not just a single machine. Michael Purvis, one of ASML's own lead technologists working on EUV light sources, has spoken fairly openly about how hard the company is currently pushing its existing tin plasma design toward 1,000 watts and beyond. That confidence is completely earned. ASML has, after all, already solved a version of this exact problem once, over 3 brutal decades. But it is, unmistakably, the confidence of the incumbent, the one company with everything to lose, betting that its current, deeply mastered approach stays on top indefinitely. So let's come all the way back to where this started. One company, one small town in the Netherlands, one almost impossibly hard part to manufacture that the entire modern world quietly runs on, and an entire geopolitical strategy that was built, brick by brick, specifically to protect it. Neither of China's answers breaks that monopoly today, and it's entirely possible neither one fully breaks it for another decade or longer. The loud one, the brute force domestic prototype, sprawled across a factory floor, chasing both ASML's own tin droplet method and a 20-year-old discarded alternative at the same time, doesn't need to beat ASML outright. It only needs to beat what China is currently stuck using instead, and by that far more modest standard, it's already closer than most outside observers expected. The quiet one, a beam of electrons circling a ring in a physics laboratory, radiating light through a mechanism nobody had ever actually demonstrated working until a small international team proved it in Berlin, doesn't threaten ASML's market share today at all. What it threatens is something deeper and slower: the quiet, foundational assumption that there was only ever one physical road to this specific kind of light in the first place. And that's really the whole lesson sitting underneath both of these stories. Once you strip away the specific numbers and the specific institutes and the specific names, ASML's advantage never actually came down to being unbeatable in some abstract sense. It came down to controlling a single, narrow bottleneck better than anyone else alive. And a monopoly built entirely on a bottleneck only ever lasts exactly as long as that bottleneck does. Somewhere on a factory floor in China, engineers are trying to brute force their way through it with scale, tin, and sheer persistence. Somewhere in a physics lab, a different team already proved there might be a second road running around it entirely. Neither path has reached the destination yet. But for the first time in 30 years, there are officially two roads being built toward the exact same light. And ASML, for all its billions, doesn't get to choose which one wins.